for the problem number 2, I guess I told you that would be the potential candidate for the field problems. And most likely, they might appear again in the final exam in some modified form. So try to do as homework again for final. So something, the problem with not exactly the same, but similar form of a logarithmic derivative will be most likely given for the final exam. Okay? So I guess if you miss this time, what you can do is try to do it homework. So preparing for the compensation for the final exam. And I guess maybe I hope more than half got the first problem right. And maybe I can spend some time to solve it for you. So the question was something like this, right? 10, 6, 8. And the idea is, so matrix A is not Hermitian, right? Definitely. It's not Hermitian matrix. So the idea is to represent it in terms of some kind of this matrix is actually diagonal. That's the idea, right? So the first step is, so actually I itemized the problem. So if you just follow my instructions step by step, then I think most of you could get it right. But still, the polar decomposition is a very difficult subject. And the polar decomposition could be very important for the deep learning. So it's very important applications. So let's check with this. So we can start with M. A plus A dagger A. So 110. So you take the transpose 10, 0, 6, 8. 10, 6, 0, 8, right? So this is 110, 100, 60, 60. 36 plus 64 is 100 again, right? So this is 10, 6, 6, 10. So first step is to show that this is Hermitian, right? So this is Hermitian matrix. So if it is a Hermitian matrix, then it satisfies several properties, right? Eigenvalues are real, normalized eigenvectors are orthonormal to each other, and the matrix can be expanded by the spectral theorem, and any function of matrix can be represented in terms of a spectral theorem as well. So you can represent the square root of M. So M, 10, 6, 6, 8. So first step is to find the eigenvectors and eigenvalues. So 10 minus lambda, 6, 6, 10 minus lambda. 10 minus lambda square minus 36. 10 minus lambda plus 6. 10 minus lambda minus 4. So 16 minus lambda, 4 minus lambda. So lambda can be 4, 16, right? So we can start with lambda 1 is 4. Then we need to find the normalized eigenvectors. So m lambda 1, 4. So 10, 6, 6, 8, x, y, 10x plus 6y, 6x plus 8y is 4x, 4y. No, it's 10. 10. So x plus y is 0. So we can set as a lambda 1 square root of 1 minus 1, right? Lambda 2 is 16. So m lambda 2 is 16 lambda 2. So 10, 6, 6, 10, xy, 10x plus 6y, 6x plus 10y is 16x, 16y. So that means x equal to y, right? So for lambda 2 can be square root of 2, 1, 1. So we can summarize m 10, 6, 6, 10. Lambda 1 is 4. Lambda 1 tilde, square root of 2, 1 minus 1. Lambda 2 is 16. Lambda 2 tilde is square root of 2, 1, 1. So actually, square root of m is what? Square root of lambda 1 tilde, lambda 1, right? Square root of 2, lambda 2, lambda 2. So that is square root of lambda 1 is 2 times this is 1 over 2, 1 minus 1, 1 minus 1, plus 4 times 1 half, 1, 1, 1, 1, right? So that is 1 minus 1 minus 1, 1 plus 2, 2, 2, 2, 3, 1, 1, 3. That's your square root. And we need to find the unitary matrix, and that can be done by this way. Psi 1 is A times lambda 1 tilde, right? Then square root of 10, 10, 6, 0, 8 times square root of 1 minus 1. Square root of 20 times this is 10 minus 6, 4 minus 8, right? So this is square root of 5 over 2 minus 4. And we can define E1 as square root of lambda 1 psi 1 is square root of 5, 1 minus 2, right? Am I writing too fast? No, it's okay. Because you you just solve this problem, you can follow very easily. For I-2, call it 3, 1. Check. Psi 2 is 8 times lambda 2. Square root of 10, 10, 6, 0, 8. Square root of 2, 1, 1. Square root of 20. That is 16. 8, right? So that is square root of 5, 8, 4. E2 is actually lambda 2 over phi 2 is square root of 5, 2, 1. So let's summarize. We have lambda 1 square root of 2, 1 minus 1. E1 is square root of 5, 1 minus 2, I think. Lambda 2 is square root of 2, 1, 1. E2 is square root of 5, 2, 1. So we define U as E1 lambda 1, E2 lambda 2, right? So square root of 5, 1 minus 2. No. Sorry. What? 1 minus 2, square root of 2, 1 minus 1, square root of 5, 2, 1, square root of 2, 1, 1. So that is, we can put them together with the square root of 10, 1 minus 1 minus 2, 2, square root of 10, 2, 2, 1, 1. So square root of 10, 3, 1, 1, 3, right? Minus 1. So we can check. Square root of m was 3, 1, 1, 3, right? So U square root of 10, 3, 1 minus 1, 3, 3, 1, 1, 3, square root of 10, 3, 1, 10, right? 3, 3, 6, 0, 8, which is A. I didn't ask, but also you can 1, so this is 1, 2, 3, 4. Actually, you can show that this is U inverse. And I didn't ask you because it may take too long for this problem, so you can do it as a homework. So, how many of you think you get it right? There's this problem. 1, 2, 3, 4. 5? Only 5? 6, 7, 8, 9. Okay, good. So this is a very simple example, but this is a very good example for the polar decomposition. So you can actually decompose any square matrix into the product of unitary matrix times the diagonal matrix. So I would think about asking you to obtain the polar decomposition for 3 by 3. But so actually I designed the problem, and it turns out that it took me for over an hour to finally decompose. So maybe a bit too difficult for you. So maybe I can leave it for final. Or still 2 by 2 can be quite difficult, right? So polar decomposition problem combines everything about the linear algebra, determinant, finding eigenvectors, use the spectral theorem, right? And matrix multiplication, everything. So you can think that polar decomposition problem is also the sure candidate for the final exam. So you have 2 very likely candidates for the final, right? The polar decomposition problem, and another one, logarithmic derivative. So before I proceed, any questions? So let's continue our discussion about the equidimensional homogeneous ODE. So assuming that we have A0x or you can transform this into the following form, right? A0 say constant coefficient A0. You can transform this into dz d minus 1, dz d minus n plus 1, yz plus a1 dz d minus 1y. Oh, sorry. Blah blah blah. dz d minus n plus 2yz plus an minus 1 dz dy plus any equal to 0, right? So we can write down the differential operator as a0 dz d. Sorry, this is dz d minus 1 dz d minus n plus 1 an plus. So we can transform into the following form: B0 dzn dn B1 dzn minus 1 bn. So for example, maybe going a little bit too fast, so I'll let you catch up with it's my handwriting. I know I'm writing very fast, so that's old habit. Very difficult to fix. How about, am I talking too fast or is it okay? So it's my handwriting. That's fast. Okay, so as an example, consider the following example. For example, L is dx squared a dx dx plus b. So it can be transformed into the following, right? dz minus 1 plus a dz plus b. So dz squared d squared plus a minus 1 dz d plus b. So for example, a is 4, b is 2. Then L is simply dz squared 3 dz d plus 2, right? So we can try L exponential lambda z as trial solution. So lambda squared plus 3 lambda plus 2 exponential lambda z is equal to 0. So lambda is minus 1 or minus 2, right? And z is nothing but the ln x. So general solution is the following. C1 exponential minus ln x plus C2 exponential minus 2 ln x. This is actually C1 x minus 1 plus C2 x minus 2. Another case, what if using a equal to 1, b equal to 1. Then L is simply d squared 1, right? So L exponential lambda z lambda squared plus 1 exponential lambda z is equal to 0. So lambda has to be plus minus I. The solution is actually C1 exponential I ln x plus C2 exponential minus I ln x. So this can be rearranged into D1 cosine ln x, D2 sine ln x. So exponential I something can be written as a sine and cosine with different coefficients of course. So this is a tricky case. And another case is so this is more actually more convenient form. And what about double root? For example, A equals 3, B equals 1. Then L is simply dz square 2dzd plus 1, right? So L exponential lambda z is lambda square plus 2 lambda plus 1 exponential lambda z is equal to 0. So lambda plus 1 square exponential lambda z is 0. So we can apply the same analysis. So if lambda z minus c is a solution, then z minus exponential minus c is also a solution, right? Because partial lambda partial L exponential lambda z is also 0, right? So exponential minus c is exponential minus ln x is 1 over x, and z exponential minus c is ln x exponential minus ln x is 1 over x ln x. So general solution will be c1 x inverse x to the minus 1 plus c2 ln x x to the minus 1. So at least the ordinary differential equation with the constant coefficient and also ordinary differential equation, equidimensional ordinary differential equation can be solved exactly for the homogeneous case. And the next step is to consider the inhomogeneous case. And I think maybe we can leave it for next week because you have done a lot of work for taking the quiz. So if there is no objection, I'm going to stop today. What do you think? So you can enjoy your lunch.
중간고사는 전범위인가요?
전범이요.
그 파이널 테스트에서 혹시 전범위로 보는 건가요?
전범이.
아, 그럼 문제 수는 어떻게 되는지 혹시 알 수 있을까요?
3시간 정도 볼 거예요.
아, 3시간 정도 보면 충분하게 많이 나오겠네요. 전범위 나오겠네요.
뭐 한 대여섯 문제 나오겠죠?
네. 문제에서 m이 a 대거 a인데 m은 a 곱하기 a 대거로 놓고 풀었으면은 밑에 문제가 쫙 틀리는 거예요. a 대거 a.
이렇게 풀어도 되는데 그러면은 A가 이렇게 되는 거야.
네네네.
네. U가 뒤에 와야 돼.
아 이거 같은
이렇게 풀었으면 맞게 해줘야 되지 않을까?
부분 좀.
근데 부분점수 있을 것 같은데. 근데 문제에서 정확하게 A 대거 A를 풀라고 했으니까 일단은
네 그건
거기서 일단은 문제를 정확히 안 푼 거니까.
네 그 밑에 부분 좀.
네.
감사합니다.
늦게 온 친구는 안 찾아오네.
그냥
그렇지.
너무.
I think